Welcome to Video Wissen. We have a talk given by Roelof de Jong, who is a project scientist and principal investigator of FOREMOST. This is a spectrograph which will be used at the VISTA telescope in Chile. Roelof has given this talk in the talk series Babelsberger Sternnächte, and he's a member at the AIP, the Leibniz Institute for Astrophysics in Potsdam. And this institute is also a member of FOREMOST and responsible for that. So have fun and don't forget to like the video.
So welcome here at the AIP, where we're going to talk about FOREMOST, a new wide field spectroscopic survey facility that we're building here in this very building. I'm Roelof de Jong and I'm the principal investigator of this new instrument. So what is FOREMOST? FOREMOST is going to be a broad range of things where we're doing both the science and the instrument all together. So we're working on the science, where we have a broad range of science that we're going to do for a telescope that is in Chile at a telescope observatory that we call Paranal. And with this telescope and this new instrument, we will study a broad range of topics like black holes, dark matter, dark energy, but also the formation of galaxies and especially also our Milky Way. And so we're going to talk a bit about the technology that we're developing for this and how we operate this instrument, because that's also quite unique. And finally, I'll say a little bit about that location, Paranal. So let's have a look. We're talking about spectroscopy here. Most of us understand spectroscopy quite a bit. If we put light through a prism, we get the colors of the rainbow, which is basically what white light is made of, different colors that we can see. And with our instruments, we can record that. And so if we look at this spectrum of an object, we can learn a lot about these objects. We can learn about the temperature of a star, or we can learn about its velocity. We can actually learn a lot more. We can learn about the chemical composition of the star, or if we're looking at galaxies and look at the spectrum of galaxies, we can look at the star formation history in such a galaxy, or we can learn about the velocities of the stars in a galaxy. So it's very interesting to get spectra of objects in the Milky Way and in galaxies beyond. Of course, if we take one spectrum at a time, it takes a long time before we have a lot of objects. So the idea of FOREMOST is not look at just a few objects one by one, but look at a lot of them, all at the same time. So with FOREMOST, we can look at almost 2,500 objects every time we put the telescope somewhere on the sky and learn a lot about different science. So here are the main topics that FOREMOST wants to address. We want to understand the cosmology of the whole universe. We want to learn about what we call the high energy sky, things like black holes that bring out a lot of energy, or colliding clusters of galaxies. Or we want to look at the galaxies themselves. How do galaxies form and how do they evolve? And finally, we're very much interested in our own Milky Way. How did our Milky Way get together? How did the stars in our Milky Way evolve? So let's have a look at that. We'll first look at the dark side. And the dark side are the things like dark energy, dark matter, and black holes. Basically things that we cannot really see. And so we need other objects to look at them, to see the effects of these dark matter and dark energy. We can do that by looking at millions of objects. By millions of objects, we can look at the statistics of how these objects are distributed. And then we have now found, with other measurements, that a large fraction of the universe is actually this mysterious dark energy, which we do not really know what it is, And so we want to measure more accurately what the effect is on the universe. And then there is this dark matter, which is actually some kind of form of matter, unlike dark energy, which is more, as the name says, energy. And then there is this small fraction of the universe, it's only 5%. That is what we call normal matter, what we see around us, what we can touch and hear and feel. But there's other components, there is new physics there that we do not fully understand. And to get to that bottom of that, we want to measure a lot of objects, getting at the scale of the universe. So one thing we can do to measure that expansion and the scale of the universe, we have now discovered that the universe is accelerating. Instead of slowing down as we had originally expected under its own gravity, the universe is moving out faster and faster. But how do you measure that? Well, one way of doing it is that we see how the universe under gravity is clumping together. That's the structure that we see here in the background. And that clumping has a very particular scale when the universe is expanding. There are sort of bubbles in there. And these bubbles, to measure these bubbles, we have to look at thousands and millions of galaxies and measure accurately the position in the universe. And if you then look back in time, you can see how the universe was smaller in the past. And these bubbles were smaller in the past as well. And those statistical structures, this is what we want to measure with foremost. But because it's very vague structure, you need millions of galaxies to measure this. And that's where foremost comes in, where it has the capability to look at the distances of millions of galaxies. So hopefully with foremost we get one of the most accurate measurements of this expansion of the universe. The other part of the dark side is dark matter. And so dark matter is also everywhere in the universe and is slowly clumping together. And at the places where it clumps together, it will make galaxies. But the structure and the nature of this dark matter, there are many theories about that. How would that look like on the smallest scales when clumps get together and to form galaxies? And here are some different models that show there is different structure depending on your dark matter model. And so this is what we're going to do. Also on small areas on the sky, we're going to measure a lot of galaxies. Also galaxies close together. And depending on the properties of these galaxies and how they cluster together on small scales, we learn more about the properties of dark matter. Again, in the small areas of the sky, millions of objects to understand the structure and the evolution of galaxies and dark matter. So what we also want to look at is black holes. And black holes in itself are dark as well. No light can escape from black holes. That's what we learn. But of course, in the environment of black holes, a lot is happening. Gas is falling in and glowing very hot. Stars are affected there, star formation is happening. So we can find these black holes and we can measure them with our spectra. And very interesting is then how that the most massive black holes that we find in the centers of galaxies get there. It's not so easy to make a black hole that big. And so one theory is, of course, that smaller black holes collide together to build bigger ones. And so if you look at the plot on the right here, we see what we call a merging tree of black holes. And time goes from top to bottom, and by smaller black holes merging together, we're getting bigger black holes. And so we want to study the evolution of black holes by looking at black holes at very large distances and taking spectra there and comparing them to those in more nearby galaxies. We can see how these black holes grow over time. And this is one of the things, of the many other things that we want to do in studying black holes with foremost. And then let's move to the bright side of things, the things that really emit lights. And we're thinking about stars and galaxies. So here we want to study how galaxies evolve, but also understand the Milky Way and its nearby neighbor galaxies. We want to understand how the stars in our Milky Way evolve and what kind of chemistry is happening there. And then finally, many of the stars we believe now have planets. So if we study stars with planets, how do these stars compare to other stars in the Milky Way? And we want to understand the evolution of stars and planets together. So let's have a look how galaxies form, and in particular, how does our Milky Way form. Our models show that galaxies form when dark matter starts to clump together under its own gravity and starts pulling in gas into these dark matter clumps. And in this gas, new stars are forming. And while these stars are forming, at the end of their lifetime, they explode and bring in new gas in the galaxy. But the gas has changed. There are new chemical elements now in this gas. And so if we form new stars from this new enriched gas, which has new chemical elements, we get a different kind of stars, which we can measure with our spectra, that there are new chemical elements in these new stars. And so over time, we can follow the history of star formation and how chemical evolution happens in a galaxy. At the same time, new galaxies fall into the Milky Way, which is a pretty big galaxy, and it collects smaller galaxies around it. So both the evolution of the gas and the stars in the Milky Way, as well that history of collecting other galaxies, we want to study. And one way of doing that is that these small galaxies that fall into the Milky Way will get torn apart under the gravity of the Milky Way and form very long streams of stars that are spread over the sky but have a coherent moving. By tracing these star streams, we can learn a lot more about the Milky Way. We can learn about these galaxies that fall in, but by the gravity that is acting on these streams, we learn also about the total mass of our Milky Way. And then, of course, stars are being stirred within the Milky Way with its nice spiral arms, as the model on the right shows. And so we want to trace how that movement is and how the stars are moving in the Milky Way. And the Gaia satellite that is measuring the motions of stars around us has done an excellent job. The only problem is it's a fairly small telescope. It cannot see so far. So this picture on the right there, now I've shown the area of the Milky Way where Gaia can accurately measure the movements of stars. But if I lay next to it the area where the foremost can measure the movement of stars, you can see that we basically cover a large fraction of the Milky Way. It's a bit of a half, because we're only on one half the sky. We will be in Chile in the south of part of the hemisphere. We cannot see in the north, but that part of the sky we can see basically stars throughout the Milky Way and measure accurately how stars are moving and chemically evolving throughout the Milky Way. And then we want to look also at those stars that have planets. So there will be special missions, satellite missions are planned by ESA to measure very accurately for a large number of stars whether there are planets rotating around it. And they measure that by having a little dip in its light when a planet goes in front of its star. But then we want to know more about this star. Once we know that there is a planet there, we want to know the chemical composition of that star, and we want to know the size and the mass and all these kind of things. And especially also, how did it get here? What was its evolution? How does it connect to the rest of the Milky Way? So for that, this combination of this satellite mission Plato that is going to be launched in a few years with Foremost brings a lot of extra information about stars and planets. So let's see, where are we going? So we're going to the Parallel Observatory in Chile with our new instrument on this telescope, the VISTA telescope. It's a large 4-meter class telescope, and that's good, of course. The bigger the telescope, the easier it gets to look at faint things. And here is a picture of the number of things that we're going to put new on the telescope. And so we have to put a lot of new things, and I'll go through the different components in a second. But the main issue is we want to create a very large field of view so that we can look at a large fraction of the sky in a very quick way. And we want to look at a lot of objects at the same time. So we have many fibers that we can move around in the telescope that collect the light, and that glass fiber will take the light to our 3 new spectrographs. And these are big spectrographs so that we can handle hundreds and hundreds of objects at the same time. So let's have a look at that. This is what the telescope looks at the moment before we put the new foremost instrument on there. And what is actually hanging there, that black tube that's hanging there in the air, is the current camera that is on this VISTA telescope. And so we're going to take that camera out because we don't need it, and it has a too small field of view. So let's take it out. This is the new camera basically that we're going to put into this telescope that creates this very large field of view so that we can look at a large fraction of the sky. It's one of the biggest lenses in astronomy ever created. That front lens is almost 1 meter in diameter. And there are a whole set of lenses there. This whole system weighs quite a lot of time. And so we have a very careful system of transporting this system to the telescope. And this is higher in our integration hall here at AIP, where we're testing putting this instrument on the telescope. Of course, it's a very expensive equipment, so you want to be sure that everything goes right. So talk about that large field of view. What are we talking about? Everybody knows Orion. Orion with its 3 bright stars in the center and 4 stars around it. So this hexagonal field of view, this is what foremost can see at one time. And with such a large field of view, of course, you can quickly make a whole mosaic of the whole sky. And to put that a bit more in perspective, this is our field of view, and it fits 5 moons across. So if you look at the sky tonight and you see the moon, foremost can look 5 times bigger area on both sides. And with such a large field of view, we can cover the whole sky in 5,000 different pointings. We do probably about 10 per night. That means in 500 nights we have looked at the entire sky. Now, once you have this big telescope with this very large field of view, you want to make sure that you look correctly at all the stars and galaxies. So once we have this very large field of view, we want to make sure that our images that we're looking at are perfectly stable and sharp. And for that, we have a few extra cameras that we put at the edges of our field of view. And these cameras, as seen here, there are 6 extra cameras. 2 are basically making sure that we're following the stars as they move across the sky, while the Earth is rotating underneath. And the other 4 are basically for keeping focus, making sure that the images are sharp. And they keep also the mirror into good shape. So this is basically, if you think of a normal camera that you have been using, the image stabilization and the focus, and we're building big cameras just for that. But then we're getting to the heart of foremost, the heart of the machine, where we collect the light that is creating that telescope is making a big image for us, almost a ½ meter across, in the center of the telescope. And now we're putting glass fibers on there. And these glass fibers are tiny. They're the size of a hair. And we have to position our fibers to 1/10 of that accuracy, 1/10 of a hair precision. We have to move our fibers around. So how are we doing that? The picture at the top shows how we have a spine, or maybe we should call it a magic wand. There is a little ball at the bottom of it where around this spine can rotate a little bit. And we have an electric mechanism that we can resonate, and then we can move the spines back and forth. And so in that way you can create patterns that show you how the spines move in different objects. Actually, this video is doing the other way. We're actually going now back to the home position. They were at a different position to look at objects, and now they're going all back to a straight position. And we want to do this quickly, because while we're doing this, we cannot observe. So we're doing this all at the same time, and within 1.5, 2 minutes, all the fibers are at the new position, and we can make the next observation. And here, this shows the hexagonal field of view that Foremost has, with all these 2,438 fibers at the same time. So once we have collected our light in the fiber using our fiber positioner, the rest of the fiber has to go to the spectrographs. And fibers made of glass are very fragile, and they're very thin, the size of a human hair, so they can break easily. So we have a whole careful system of tubes that can move around to bring the light from the center of the telescope down to the spectrographs that below the telescope. And so that whole system, it's pretty big, but has to rotate and move around while the telescope is following the stars across the sky, because the Earth is rotating underneath. And so we have built a whole big system to just hold the fibers around while the telescope is moving. And that's a lot of work, putting almost 2,500 fibers one by one through all these fiber cables and making them sure that they are exactly at the right spot when they get into the spectrograph. And then we get into the spectrographs. So these are magnificent pieces of work as well. They're very large. We're talking 2.5, 3 meters diameter with large optical elements. And so each of them can hold 800 fibers at the same time and take spectra of 800 objects at the same time. And we have to keep everything very stable, because if things move around, then we cannot make accurate measurements. So these spectrographs are thermally stabilized, and we try to keep everything very stable and very fixed. There are 3 arms in each spectrograph to break the light in 3 different parts, in a red and a green and a blue. And each of that arms have a huge 10 centimeter by 10 centimeter detector, which has 36 megapixels, so more than 6,000 by 6,000 pixels in each detector, to collect this light, this very, very faint light coming from the universe. Here are some pictures of what we call the high-resolution spectrograph. We have 2 types of spectrograph. One that breaks the light out in a bit more detail. Then you need brighter objects to look at them, but you get more details, and you know even more about the chemical composition of stars, for instance. And we have already taken pictures in the lab with this spectrograph, and it has very nice quality. For instance, at the bottom you see some spectrum of the sun, and you see these little black lines in there. These are all features in this spectrum that come from chemical elements that are on the sun. And we want to do this for many, many stars. Similarly, we have 2 low-resolution spectrographs that break the light up in a bit less detail, but they cover a very large wavelength range, all the way from the very blue 370 nanometers all the way to 950 nanometers. And here are again some pictures and our very efficient people putting it together. And we have also with these spectrographs taken already test spectra, and we know that they are very good quality, so we're going to have very good quality spectra once we're on the telescope. I mentioned already we're going to operate this telescope in a bit different way than people normally use a telescope. Normally you use a telescope to look at one object at a time. Here we have, as I explained earlier, many different science cases. And some of these objects are very rare and we take only a few while we're looking at the sky, while others we want to take thousands and thousands. And so all these different science cases, all these scientists have different objects they want to look at. We all throw them in a big pool, and every time we point the telescope, we put these targets in the field and we take an observation. So we can take many different science cases for different research at the same time. And so we take one field as shown here, that's hexagon field. We put all the fibers on the different targets, take an exposure, and then move to the next. And that you do through the night, and every night we take about 10, 20 fields. And in this way, we can do about 5 million objects a year. And we're planning to do a 5-year survey where we have at least 25 million, maybe 30 million of objects that we will have observed, for which we then have excellent spectra and can do all our statistics that we need. And once it's completed, we get this kind of map of density of targets that we have observed. And some people who know the coordinates here on the sky will recognize that at the bottom right we have these 2 red spots. These are the Magellanic Clouds. We're going to take a lot of objects in the Magellanic Clouds. Well, at the left we have a part of where's the Milky Way center, also a very exciting part to look at this part of the sky. Where are we going with this? We're at the moment putting our last pieces together. We're going to test for the next few months that Foremost is perfectly working. Once we have done that, we're going to ship everything to Chile and move it up the mountain and put everything back together again. And hopefully around this time next year, we will take our first spectra and make sure that everything is working. We're going to do more tests to make sure that also all the operations are working and that we get the kind of quality of data that we need. And therefore, sometimes in the fall of next year, we will start for earnest with our first 5-year survey and hopefully many 5-year surveys after that. To wrap things up, I've been telling about the science that we're doing with Foremost. Everything from the dark side, dark energy, dark matter, black holes, to galaxies and stars, and even a bit working on planets. Then I hope you enjoyed looking at that hardware that we're building together. It's incredible technology that is of the highest standards to get to these kind of details that we need. And I'm incredibly proud of my team that has been putting this together in the last few years. We're working very hard to make it all possible to work on this and schedule the observations and look at all that data. We have more than 600 scientists who are eagerly waiting for this data. And so I can't wait to move all of this to Chile and Paranal and start looking at that southern sky. I think that we're going to have an incredible instrument that will provide unique science. We're here in the main integration hall where Foremost comes together, where we test all our subsystems before we bring it to the telescope in Chile. And we want to make sure that everything functions because it's very expensive and very difficult to fix things in the middle of a desert. So we do everything in Europe before we go to the telescope. So the system here is to take measurements of the alignment of all the components that go into Foremost. And in particular this part, We see some of the cameras in here that help us follow the stars on the sky and to get very sharp images into the fibers. And what we are also having here is a system that looks like a copy of the real fiber positioner that we use. And this helps us to test the whole telescope system before we put the fiber system on there. So the cameras we're looking at are these boxes here, and they have a little prism that they can look upwards to the sky. This is going upwards towards the sky. So here we see the heart of Foremost. This is where all the light from the telescope that will be around this heart of the telescope and catch all the light and we'll bring it into focus and create an image onto this part of the telescope. And there we see many, many thousand, 2,500 fibers sitting in tiny spines that can move around to pick up the light from different objects that are in this image that will be created there. And we can move these spines with an incredibly accuracy. Because the fibers are only the size of a hair, and we want to put our objects onto these fibers, we have to push these fibers to an accuracy of 1/10 of a hair diameter. And do that in a very quick way so that we can quickly go to the next objects. So this whole 2,500 fibers we can position in a bit more than a minute. And we can start the next observation. What we see here looks like a big black box, but what is in there is a spectrograph. Here we use the light that comes from the telescope and split it up in all its colors and have big detectors in there to register all the light coming from these objects. And we have not one of these big black boxes, we have actually 3. I would love to show you the insides, but once we have closed it, we don't want to touch it anymore. We don't want to have any dirt in there because it's highly sensitive equipment. And this particular one we call a low resolution spectrograph. It doesn't bring the light in its parts extreme version, but we have also a high resolution spectrograph where we stretch the light in all its colors even further so we can see very special details in the objects that we are observing. What we see here is the cable derotator. When the telescope is following the objects across the sky, where the Earth is rotating underneath us, then the whole telescope moves and we have to rotate the field. And while we're doing that, we have to make sure that all our fibers and all our electronic cables and the cooling system can follow the rotation without getting tangled up. And that's why we're using a system like this that protects the whole system, all the cables, all the fibers, while it rotates on the telescope. This is the backside of the fiber positioner. Here is where all the fibers come out and will connect to the system that we will show later. And what we also show here, it is positioned on the simulator of the telescope. And this shows a bit of the size of the telescope. Even though I'm pretty tall, I cannot reach to the instrument. And this is how we have to work once we're at the telescope, because the telescope itself is even much bigger. It's 4 meters diameter and goes up all the way to the ceiling here. And that's why we have this test system here, so that we can simulate the telescope and really practice how to work on a system that is much bigger than what we normally used to. We're 3 months later, and we have now built the system together in our integration hall in Potsdam. And what you see here is the backside of the fiber positioner. And outside that fiber positioner are now coming all the fiber bundles that are sitting in these black conduits. So we have 2,500 fibers coming out here at the back, going around here, and then to the spectrographs. And inside here, at the fiber positioner, we have these tiny spines, or sometimes we call them magic wands. And how do these work? So you have a little ball here at the bottom where they can turn around, and they are held by a little magnet. And then we have an electric force working on a piezo that can resonate this spine and move them back and forth so that we can put them exactly at the star or the galaxy that we want to observe. So we have almost 2,500 of these tiny spines that work all together to take the next exposure. In about a minute we can put them all at the right position. What we have here is our wide field corrector. When we have a normal telescope with big mirrors, it would only make a very small field where we can look at the stars. But with foremost, we want to see a huge area of the sky, and so we need a wide field corrector, as we call it. It's basically something like a wide angle lens on your camera. So here, it really is a big lens. This lens is almost a meter, 90 centimeters diameter. That's a big lens, and these kind of lenses, and there are 6 of those in here, are not easy to make. Specialists in the world are needed. So the glass for this camera was made here in Germany and also partly in America. Then everything was shipped to New Zealand, where the glass was made into shape. Very, very perfect, accurate shape. There the travel didn't end. The lenses were shipped to America to put a very fine coating on it. And coating, just like on your cameras, that gives it a little bit of a purple shine. Then the lenses were shipped back to New Zealand to test that the coating was actually correct. Then the shipment went on. We sent the lenses to London in England, where they were stacked together and very accurately aligned to a fraction of a millimeter. They're actually put to each other's position. And finally they arrived here in Potsdam, where we're testing everything. And then of course the travel is not ending yet. They're going to go to Chile. So in the end, these pieces of glass have traveled about twice around the world before we start using them. And mentioning how big this lens is, I would argue it is at the moment the biggest lens in Potsdam, and that's not an easy feat because Potsdam is also home of the Große Refraktor, which is the 4th largest refractor or lens telescope in the world. So I'm pretty proud that we have a very, very big lens here. What we see here is the detector system of one of the spectrograph. And actually there are 3 detector systems here, because we first split the light that comes from the objects into 3 parts. We have a blue, a green and a red arm, as we call it, in the spectrograph. And in that spectrograph we then split the light up of the objects in even smaller details, so that we can see all kinds of features in the light that comes from our objects. And so we have 3 detector systems here. Each of them has a very big CCD detector, similar to what your camera is doing in your iPhone, but we're having much bigger detectors, so it's much more sensitive. We have a detector that's almost 10 by 10 centimeters and is 36 megapixels. And why do we have this huge system around it? Well, what we need to do to have the most sensitive observations is to cool these detectors really down, so that they don't have intrinsic noise, as it's called. And we can make very sensitive observations. So there is a whole cooling system to cool it down to 110 degrees, minus 110 degrees Celsius, liquid nitrogen temperature. And there is a whole system that keeps the vacuum, so that we don't lose this cold system. So hence we have this whole system to cool the things down and to keep the vacuum around these detectors. So this shows the whole system at the back end of the telescope as it will be installed in Chile. And this whole area can rotate back and forth while the telescope is following the objects on the sky. And so the whole fiber system has to be able to run through here and keep being protected, not breaking these fragile glass fibers. And once it's coming off the telescope, it moves to the side of the telescope and then down, where it has to also adjust for going the telescope up and down, not just rotating, but also going up and down. And that's where the cables down here go, and then they move on to the spectrographs. So thank you very much for joining us here in AIP to look at the foremost system as it is being built to go to Chile. And if you have any questions, please don't hesitate to ask here in this channel.